Hello there. So for today, we will look into the graph of simple harmonic motion. Okay, problem solving. So for example 9.5, we have a displacement of an oscillating object as a function of time. Okay, shown in figure 9.10. Okay, from the graph above, they wanted to determine for this oscillation the amplitude, period, and the frequency. For B, angular frequency, and C, equation of displacement as a function of time, and then D, equation of velocity and acceleration as a function of time. Okay, so for question A, they wanted to determine amplitude, period, and frequency. This one we can obtain straight away from the graph, okay, where the amplitude will be the maximum displacement. If you observe at the graph, the maximum displacement over here will be 15, right? Okay, and then the period will be the time taken for one complete oscillation. So over here it starts from 0. Okay, you have a positive amplitude and then goes down to a negative amplitude and it returns back to 0 at 0.8. Okay, so that will be the period. Okay, so once we have the period, we can calculate the frequency. Okay, so for the solution, so from the graph we obtain the amplitude, okay, converted into meter, which will be 0.15 meter, and period 0.8 second. So from there we can calculate the frequency, okay, which will be 1.25 hertz. And then for the angular frequency which will be omega, okay, 2 pi f or 2 pi over period. So replace in, we will get 2.5 pi radian per second. Okay, from the graph, when t is equal to 0, x is equal to 0, therefore we don't have any initial phase. Okay, so 0 initial phase, that means from the general equation, a sine omega t plus with initial phase 0, so therefore we will end up with x is equivalent to 0.15 sine 2.5 pi t, where x is in meter and t is in second. Okay. So for the equation of velocity as a function of time, okay, what you have to do is that differentiate, okay, dx over dt, so which will end up with equation of velocity which will be equivalent to 0.375 pi cos 2.5 pi t. Okay, so v is in meter per second and t is in second. And for acceleration, okay, we do differentiation, okay, dv over dt. Okay, so we differentiate velocity toward time, so which will end up with function of sine. Okay, cos you will get negative sine. So simplify, that means acceleration you will end up with 0.938 pi square. Okay, so you have a negative in front. Okay, sine 2.5 t. So this one acceleration meter per second square and t is in second. Next example, example 9.6, we have a versus x graph. Okay, so figure 9.11 shows the relationship between acceleration and its displacement x from a fixed point for a body of mass given 2.5 kg and which executes simple harmonic motion. They wanted to determine the amplitude, period, maximum speed of the body and total energy of the body. So for the amplitude, we can look at the maximum displacement, which you can determine from the graph. Okay, so if you observe over here, maximum displacement, which will be equivalent to 4 centimeter, right? Okay, so we look into the solution. Okay, mass given. So the maximum displacement 4 centimeter, convert into meter. And then from the graph, maximum acceleration, okay, we can obtain 0.8, okay, meter per second square. And then using the equation for maximum acceleration, a maximum will be equivalent to amplitude times omega square. So from there we can determine, okay, replacing the value, we can determine the value of period lah, okay, which will be equivalent to 1.40 second. Okay, or the gradient, okay, if we just do comparison lah, okay, comparison, a will be equivalent to y-axis and then x will be equivalent to a, right? Okay, amplitude. So therefore gradient will be equivalent to negative omega square. So if we calculate the gradient, also we can determine the period. Okay, so for C, okay, by applying equation of maximum speed, okay, we already have determined the value of omega, so we can determine the maximum speed. And then for the total energy, just apply the equation for total energy, okay, replace in the value, and then final answer we will end up with 4.03 times 10 to the power of negative 2 joule. Okay, example 9.7, you have a figure 9.12 shows the displacement of an oscillating object of mass given 1.3 kg varying with time. The energy of the oscillating object consists of the kinetic and potential energy. They wanted to calculate the angular frequency of the oscillation and then the sum of these two energy. Okay, so this is considered quite straightforward question. Okay, so for the angular frequency, first what we can do is that we can determine the period from the graph. Okay, from the graph, amplitude given and then period also given. So the angular frequency will be equivalent to 2 pi over period, so which will end up with pi over 2 radian per second. And then to calculate the sum of the kinetic and potential energy, we use the equation of the total energy, okay, which will be equivalent to half m omega square a square. So just replace in the value and final answer we will end up with 6.42, okay, times 10 to the power of negative 2 joule. Okay, example 9.8, you have figure 9.13 which shows variation of displacement x with time for an object in simple harmonic motion. They wanted to determine the amplitude, period and frequency of the motion. So this one, I think you can refer back to the first example, okay, how to obtain the values from the graph. Okay, so basically amplitude, period you can determine from the graph, and frequency we can calculate by using the value of the period. Okay, and then we have another simple harmonic motion leads the simple harmonic motion by a phase difference of 0.5 radian. Okay, where the amplitude and period of both simple harmonic motion are the same. So on the same axis, they wanted to sketch the displacement against time for the both simple harmonic motion. Okay, so we solve part A first. Okay, so solving part A from the graph, we can obtain amplitude, period. Okay, so from there we can calculate the frequency, which will end up with 0.5 hertz. Okay, and then we can make the equation for the simple harmonic motion for the first graph. Okay, and then since it is not starting from 0, okay, so that means you will have an initial phase which will be equivalent to pi over 2. Okay, let's say this one is x1, first one. Okay, and then you have another simple harmonic motion, okay, which leads by a phase difference of 0.5 radian. So that means you add up another pi over 2. Okay, so add up another pi over 2 with the initial, okay, so which will end up with pi radian lah. Okay, so for the equation for the second simple harmonic motion, we will end up with 4 sine pi t plus with pi. Okay, so if you plot for the first graph, okay, it will start with maximum amplitude, and then for the second graph it will start from 0, but the first amplitude you will have a negative value lah over here. Okay, and then we do the labeling.